Now we're coming to the end of the column generation procedure. So far we saw the column generation procedure solve a linear program master problem. The only thing left to do is to solve an integer programming master problem. Here we have an integer programming master problem where the only difference between the linear programming master problem is that we set the lambdas to be in the set 0 and 1. We note that from the Dantzig-Wolfe reformulation, this exactly matches the original integer programming formulation. Further, because of our implication of how to write x variables, given some set of lambda variables, lambda tildes, we can write our x tilde variables. And we should note that because xit is always an integer vector and it's constant, that the x tilde variables are going to be integer if and only if the lambda variables are going to be integer. So this equation tells us that we have integrality in the x's if and only if we have integrality in the lambdas. We're going to use this to expand on our column generation procedure so that we can solve integer programming problems. The way we solve an integer problem is we put our branching, or rather our column generation procedure, inside of a branching procedure, like branch and bound. The way we achieve this is, first, we identify whether we have an integer solution. If we don't have an integer solution, there's some lambda tilde variable that's not equal to 0 or 1. Because of the implication we just went over, this implies that the vector associated with this lambda is not a 0, 1 vector, which means that we can find at least one entry inside of this vector that's not an integer variable. Once we identify this variable, we can branch on it. That means that we can restrict our solutions to come from either setting this variable equal to 1 or setting this variable equal to 0. In our branch and bound procedure, we can view this as separating our space into two halves. One half of our feasible solutions has xij tilde equal to 1, and the other half of our feasible region has xij tilde equal to 0. For notational convenience, we're going to identify a particular variable that's not equal to 0 or 1. This is going to be the ith partition, or the ith decomposition, and the jth variable of that decomposition. We use capital I and capital J to denote that this is a particular I and a particular J, not just an index that we iterate over. So we have a particular xij variable, and it's not equal to 0 or 1. We'll go through exactly one case, where we set xij equal to 0 in our branching process. If we set xij equal to 0, we can write what this means in terms of lambdas here. Effectively, we want to say that we don't want to set xij equal to 1 in this setting. That's because we've set it in the branching process to be equal to 0. To do this, we look at all of the explicit feasible solutions, t, so that xij is equal to 0, and we make sure that our lambdas only come from this. This equation forces all the xijt's where xijt is 1 to be equal to 0. And so effectively this constraint tells us that xij can't be set equal to 1 in any of the feasible solutions that our program is going to pick. In order to inject this into our integer programming procedure, we write our integer program with an additional constraint. This additional constraint is exactly the constraint that tells us that xij can't be set equal to 1. Now, although this restricts our set of feasible solutions so that xij has to be equal to 0, we can also view it in a different way. What we've done is we've summed up over a subset of the columns and set them equal to 1. In effect, what this constraint is doing is it's excluding a large set of columns. It does this by setting a large set of variables equal to 0. So now we have an integer programming master problem, and this integer programming master problem just has an additional amount of restrictions on the columns. Now we can get an idea of how to solve an integer programming master problem. We call this the branch and price framework. The framework works by first solving the linear programming master problem via column generation. We use all of the tricks and tools of column generation procedures. At some point, we're going to terminate, and we're potentially going to have a solution that has a fractional value. We'll branch on one of these fractional variables, and we just saw that by branching on fractional variables, what we've done is introduce two new restricted problems. Then we're going to solve both of these new restricted problems, and then iterate continuously until we find an integer solution after enough branches.